So this section of work in BC Calculus takes us to parametric equations, which after we finish up sequences and series is pretty much where we're going to spend the rest of the year. So it's worth getting the basics down pat. All right, so to start, what is a parametric equation? Well, I actually want to start with this example here where it says consider a projectile whose path is given by the function y equals, negative x squared over 72 plus x. And so in this case, as it says in the next sentence, it would seem that x is the object's horizontal position, measured in feet or whatever our units happen to be, and y is its vertical position. Right, so that, for example, if I tell you that, I am almost 36 feet away from my starting point, you could say, oh, well, then it looks like, based on reading the graph, we are roughly 18 feet in the air. So that's vertical position as a function of horizontal position. However, all right, both of those components of its position, horizontal and vertical, depend on yet a third variable, which is time. And so how do we bring this third variable into play and show that each of these three components are related: time, horizontal position, and vertical position? Well, the answer, is parametric equations. All right, so parametric equations give us a way to describe a relationship between three variables instead of two. And the thing that's nice about it is that it lets us do it on a two-dimensional coordinate plane, because let's face it, that's where we do most of the math. All right, so let's now suppose that we know that the projectile's position can be described using these two equations. All right, the first, which describes horizontal position as a function of time, and the second, which describes its vertical position as a function of time. So that right there, those two equations, that is a set of parametric equations. And parametric equations will usually be given in a set, because if you only need one equation, you probably only have two variables, barring any multivariate business. So let's go ahead and use these parametric equations to determine the object's position at t equals 1. And what might not be readily apparent from this, it's not really written very well, is that these radicals actually close at the 2. So the t is not under the radical. It actually won't make a difference for our purposes, right, if we're using t equals 1, but hey, worth mentioning. Okay, so when t equals 1, all right, our horizontal component will be 24 root 2, and our vertical component at t equals 1 will be negative 16 plus 24 root 2, which, if you have a calculator handy, that's fine. You can figure out decimal approximations for those, but I have conveniently marked that point up here. All right, so this corresponds to the time when t equals 1, which really is not shown on that graph. But we do know that the ordered pair xy, would be 24 root 2 and negative 16 plus 24 root 2. Okay, so now if we come on down, and you're going to have to forgive me because they updated Explain Everything, and now moving a page is weird. So we're going to see how it goes. But if we come on down to the bottom of the page, yes, it's working. All right, we're going to formally try to define parametric equations in terms of their graph. So if f and g are two continuous functions of another variable t, all right, then x as your function of t and y as your other function of t are called parametric equations. So just to do a little bit of labeling, in this case, this is what we would be calling or considering f of t, right? It's a function of time. And this piece right here would be g of t, another function of time. So what we have here officially is x as some function of time and y as some other function of time. So there is your set of parametric equations. Okay, and then the variable t, right, which x and y both depend on, is called the parameter. And so when you sketch the graph of a set of parametric equations, it graphs as a plane curve, all right, which we usually label as C. I figure it's worth mentioning. Okay, so let's do some sketching of plane curves on the next page. Okay, so we've got a plane curve given by this set of parametric equations, x equals t squared minus 4, and y is t over 2, and then they give us a very specific domain for t between -2 and 3. So basically, what we're going to do here is go through this chart and calculate values of x and y by plugging in these given values for t. So for example, when t is -2, right, we will have 4 minus 4 for x, so that's 0. And then for y, we've got -2 over 2, which is -1. Okay, so that gives us an ordered pair, which is x equals 0, y equals -1. So we start down here. Okay, and so I'm just going to erase this for clarity here. It's not hard to see the idea behind what we're doing. All right, so now when t is -1, let's see, that is going to be -3 for x and -1/2 for y. Check my math on this. Okay, so let's see, x is -3, y is -1/2. Okay, and then when x is 0, we have -4, 0, and so on and so forth. And let's see, when x is 2, when t is 2, again, we have 0 and +1. So interesting to note, these do not necessarily graph as functions, right? We've got multiple y values for corresponding x values. Of course, the ordered pairs are unique for unique values of t, but on the coordinate xy plane, they do not necessarily graph as a function. And so then let's see, for 3, we've got, let's see, that's going to be 5 and 1.5, basically. Yep, 1.5. So let's see, 5, 1.5. Okay. So now we've got some ordered pairs, right? They should be connected by a smooth curve. And so now here is the first important thing. When we plot these, we plot them in increasing value of t. So our smallest t value was -2. And that brought us to this point. So here's t equals -2. Then we moved here. And so on and so forth. T equals 1. This point corresponded to t equals 2. And this one corresponded to t equals 3. So that is the order in which we have to connect the dots. This could make a variety of wonky graphs if we just decided that we were allowed to connect these points in any arbitrary way that we wanted. So we must start at the smallest value for t and then continue in increasing values of t. I'm not going to put arrows on because they were very specific about what the domain was. So I'm not going to put arrows on the end. However, I am going to put arrows actually on the curve so that my reader knows in which way this curve travels, right? Basically, there are two directions, right? I mean, unless I labeled, t equals -2, -1, et cetera, et cetera. If I just had the plane curve, you would want to know, well, where am I starting and where am I ending? So I usually like to just put a couple arrows so that anybody who is looking at this we'll know which way the trajectory is. And that's how we refer to it. We refer to it as trajectory. And so I took the time to make some of these important notes for you. Okay, right, so just like we said before, all right, plot points in order of increasing t-values. Use arrows to indicate your trajectory, or, what is the exact path that we are supposed to travel here. Ooh, and look at that, number 3, already mentioned it. The resulting graph might not be a function. That's okay. And then number 4, something that we will talk about more extensively later, is that there may be more than one set of parametric equations that trace the same plane curve. So a plane curve does not necessarily have a unique set of parametric equations. All right, but let's get to do a little bit more graphing, and then to wrap this all up, we'll come back and create multiple sets of parametric equations for one single curve. So now let's say you are given a set of parametric equations and you want to graph it. Yeah, we just did that, I know. But I'm looking at this, I see radicals, I don't love it. And so you have a choice. I mean, you could hoof it, right? You could take the long road. But sometimes by working a little bit smarter, we can save ourselves some time and some effort. All right, and this is helpful too, because, let's say you just want an inherent sense of what this looks like. By eliminating the parameter, all right, we can get a sense of what the graph would look like in a regular XY plane, meaning t is out of the picture. So basically, to eliminate the parameter means to express y strictly as a function of x, to reduce your set of parametric equations to just the interplay between y and x and take t out of the picture, at least for now. We always bring it back in because it's important, but just to get a sense of the shape, we bring t out of the picture and just say, all right, what's the relationship between x and y? Because that is what the curve is going to look like. So if we want to eliminate t, we should probably solve for it. All right, so I would say solve for t in one equation. I am going to choose x because I see t in one place and I feel like that's going to make my life a little easier. So let's take x equals 1 over root t plus 1. From there, I will get root t plus 1 equals 1 over x. Then I shall square both sides. So t plus 1 equals 1 over x squared. So now I have t equals 1 over x squared minus 1. And so now, you're probably figuring out how this is going to work. Let's plug that expression for t into y, which will leave us with y strictly as a function of x. So we're going to plug t into other equation. So that will give us y equals, all right, a little bit of complex fraction business, but it's not terrible. Minus 1 plus 1. Well, that's nice. That's going to cancel. All right, so that is just going to leave us with 1 over x squared minus 1 over 1 over x squared. And if I just multiply everything through by my least common denominator, which is x squared, let's see, that's going to give me 1 minus x squared over 1. Okay, so what this gives us is y equals 1 minus x squared. Oh, so it's a parabola. That's a lot easier, isn't it? Right, so that's basically just a downward-facing parabola, right, with a y-intercept of 1. So let's graph that. It's like, hey, we know what this looks like now. Okay, but now but now, because it couldn't just be that easy, I know, because there is this issue of t, and we can't just ignore it. All right, so what we have to do next after graphing, so step 3 is going to be graph. All right, we basically got to put all our ducks back in a row. So that's going to mean check our domain, check our trajectory. Okay, so as far as domain goes, we know a couple things, right? We were told t is greater than -1. All right, so let's see, come on down here. Ooh, oh boy, it's so wonky. Okay. All right, so for us, all right, our domain, all right, is -1, basically to infinity then, all right? So t must be greater than -1. So let's figure out where our x and y coordinates are going as we get close to -1 for t and as t approaches infinity. All right, so let's think. All right, and actually, let's do as t approaches infinity first. So it might be actually more helpful for us to write our domain for t. Right, I'm just going to specify this is for t. So that's from -1 to infinity. So let's see, as t gets super, 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 super large, where are our x and y coordinates going? In other words, all right, so let's see, as t approaches infinity. Okay, so basically we want the limit as t approaches infinity of our function for x, which is going to be the limit as t approaches infinity of 1 over root t plus 1. Well, as t gets very, very large, right, the denominator grows, 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 so the fraction shrinks away to 0. Okay, and so we're going to do something similar for y. All right, so then we're going to take the limit of the y component, which is, let's see, what was that? Oh, t over t plus 1. And as t goes to infinity, a couple ways you could see this. Ultimately, you could use L'Hopital's rule if you needed to. This would go to 1. So now we know that as t gets large, right, my x-coordinate is going to approach 0, and my y-coordinate is going to approach 1. So actually, this dot up here, we never reach it, right? That's the limiting value right there. Okay, so clearly as t gets large, we are approaching that point 0, 1. But now here's the question. Are we approaching from this direction, or are we approaching from this direction? So figuring out the limit as t gets close to -1, right, basically the other end of our domain, that's going to allow us to figure that out. Okay, so let's do this in a different color. All right, so basically now, and I'm going to erase this just to give myself a little bit more room. All right, so now let's look as t approaches -1. We just got to figure out, okay, we know that we end up top there, right? At sort of like the end of our domain. But where do we begin? All right, so at the beginning of our domain, at -1. All right, and we can't just plug in -1 because of obvious domain issues, so we got to take a limit. All right, so as t approaches -1. So the limit as t approaches -1, we'll check our x component first. So that's going to be, let's see, 1 over root t plus 1. And now that I look at this, I feel like we need to do as t approaches -1 from the right, because I think if we approach from the left, we're going to end up in imaginary land. So as t approaches, -1 from the right, let's see, we will end up with 1 over a very teeny tiny positive number. So effectively, infinity. Okay, so then let's check our y component. here. All right, so this is where we are at theta equals 0. Okay, and we'll actually get the same result, right, if we plug in 2 pi for theta, because 2 pi is coterminal with 0. It is in the same spot. So we probably want to check something that is between 0 and 2 pi, and I don't recommend checking pi, right, because pi would probably land us over here, and well, how did we get there? Did we go clockwise or counterclockwise? So let's pick pi over 2. All right, so let's check theta equal to pi over 2. And that'll be a little bit more informative. So x will be 3 times the cosine of pi over 2, and the cosine of pi over 2 is 0, so this is 0. And y will be 4 times the sine of pi over 2, and the sine of pi over 2 is 1, so y is 4. So when theta is equal to pi over 2, we land up there, and that's all we need. That's all we need to tell us that the trajectory is counterclockwise and that we are moving like this, one full circle. Done and done, right? Not nearly as bad as the last one. And then on the next page, you're going to love it because it's super easy. So that last page was all about graphing parametric equations and all of the intricacies that come along with that. Now, all right, we are going to be taking rectangular equations, right, functions of x and y, and translating them into parametric equations. And like I had indicated before, there are oftentimes more than one way to do this. In fact, lots of different ways to parameterize one rectangular equation. There's always what I like to call the cheat, all right, which is to basically say, all right, I'm going to make a set of parametric equations. I'm going to say, right, because if I'm making a set of parametric equations, I'm basically trying to do, all right, x is some function of t and y is some other function of t. So one really easy option that I have for that could be to just say x equals t. It's not interesting, but technically, right, and now just replacing x with t in the original equation gives us an option for a set of parametric equations. It's not pretty. It seems kind of silly, but okay, it works. So let's try something a little bit more interesting. And there are going to be a lot of different ways that you can go with this. So I will be interested to see what else you can come up with that is not just exactly like what I did. But I see one obvious one here. We could just sort of scoop up all the stuff in the denominator and be like, hey, you, I shall call you T. So in other words, we are going to let T equal x minus 1. And then from that, we get what x has to be, right? If t is x minus 1, x is t plus 1, right? And then y will simply be 4 over t. I like that one a little bit better. It's slightly more clever than the first one and a little bit more elegant, in my opinion, right? So not so bad. I'm sure you could think up some more. Honestly, besides these two, they start to get a little bit more complicated, but hey, go nuts. All right, so let's try again. Okay, so we've got y equals x squared. All right, pretty easy, like the most basic parabola. But again, our goal to find a set of parametric equations means to express x as a function of t and y as a function of t while preserving the relationship between x and y. So of course, let's get our cheat out of the way, right? We could say that x equals t and that y equals t squared. Okay, great. On to something more interesting. I could say, you know what? X squared u. you are going to be t, right? We could just say, all right, I'm just going to say that t is x squared. And so now I know what x has to be, right? From that definition, from that choice, x has to be root t. And then that leaves us with y equals t. So it's not difficult to come up with something slightly more creative. All right, but that's pretty much all there is to it, and you've got a lot of freedom here. So I feel like that was a nice light way to end the topic. And if you feel comfortable with this, then you should be all set for getting into some more complicated types of parametric equations.